Welcome to lesson 5.4, Proofs Using Transitivity. So the transitivity part of the proofs is referring to the transitive property and the idea of transversals, which we're going to get to. But remember, the transitive property is the one we have of both equality and congruence. Transitive property says if A equals B and B equals C, then A equals C. That's that main idea behind the transitive property. So the first example we're looking at is just going through the process of finishing this two-column proof in which they gave us the conclusions. We need to fill in the justifications or reasons. So just like any proof, you always begin with a conclusion that comes from your given information. Now, when I write proofs, I typically will take all the given information and write it out in step one together. Some proofs break that down based on the process they go through. For example, you'll see down here, conclusion 1 and conclusion 3, both are information from our given, so they decided to split it to steps 1 and 3. That's fine. They could have written this part 3 with 1 and saved themselves a step also. But you know you're always starting with at least one part of your given. So the first conclusion, 1, is that circle with a center A with a radius of AB. So circle A has a radius of AB. The other given that we know is circle B has a radius of BA, and then the intersection of circles A and B are points C and D. They want us to prove that triangle ABC here is equilateral, meaning all three sides are the same length. So the idea behind any proof, again, is each step along the way, you want to get one step closer to the prove statement. And then you can only do one thing at a time along the way to proving your statement. So after we said circle A with radius AB, they gave us the conclusion that the distance from AC is equal to the distance AB. So AC here is equal to AB here. How can they say that? They can say that based on the definition of a circle, which states all the points are equidistant from the center. So with C and B both being on the circle, they are the same distance from A. So AC equals AB. Then they used our given again, circle B with a radius of BA, and then they used the definition of a circle again to say that AB is equal to BC. AB here equal to BC here. Then in step 5, we're going to be using the idea of transitivity or the transitive property. And if we look back at steps 2 and 4, we can see where they got this conclusion for 5 from. In 2, AC equal to AB. And in 4, AB equals BC. So if both AC and BC equal AB, then AC equals BC by the transitive property of equivalence. And once we know AC equals BC, so AC is the same as BC, and they both equal AB, so all three sides are equal, so triangle ABC is equilateral by the definition of an equilateral triangle. So that's just one example of using the transitive property within a proof. Now we're going to go back and establish some vocabulary that we'll be using within these proofs. So one vocabulary term is a transversal. And a transversal is a line that crosses two or more lines. So looking at the diagram over here, T is the transversal, that crosses line M and line N. The interior angles are the ones that are between the two lines along the transversal. So looking at this diagram, our transversal T, the two lines M and N, so the interior angles would be angles 3, 4, 5, and 6. They're all in between the two lines. So our exterior angles are the ones along the transversal outside of the two lines. So angles 1 and 2 and angles 7 and 8 are exterior angles. And then we have two special relationships. Alternate interior angles are on the inside but opposite sides of the transversal. So 4 and 6 are a pair of alternate interior angles. 3 and 5 are also a pair of alternate interior angles. And then alternate exterior angles are looking at the angles on the outside, but they're on opposite sides. So 8 and 1 are alternate exterior, along with 7 and 2. And then we get our last type in this case, which is consecutive interior angles or same side interior. And those are both on the interior, but on the same side of the transversal. So that would be 4 and 5 or 3 and 6. And those are called same side interior or consecutive interior angles. Now, why do all these angle relationships or pairs matter? Because when we have parallel lines, so if M and N are parallel, we get a couple special properties that make up the parallel line theorem. If parallel lines are cut by a transversal, so parallel lines cut by a transversal, any pair of alternate interior angles are congruent. So if M and N were parallel, 4 and 6 are congruent, 3 and 5 are congruent. Any pair of alternate exterior angles are congruent. So 7 and 2, 1 and 8, both would be congruent to each other. And then the third part of that theorem says same side interior angles are supplementary, meaning angles 4 and 5, if M and N were parallel, 4 and 5 being supplementary, add to be 180 degrees, or they make a flat line when combined. So then example 1, we're going to look at a proof based on that idea of a transversal. So we're given that M is parallel to N with the angles as numbered. So the first conclusion, M parallel to N, the justification was given. That info is given. You'll see their last conclusion is always the prove statement. So how do we go from M being parallel to N to stating angle 6 is congruent to angle 4? Well, first, angle 6 and angle 2. Angle 6 is here. Angle 2 is here, following the transversal. They are both in the upper right, meaning they are corresponding angles, and the corresponding angle postulate states they are congruent. So angle 6 is congruent to angle 2 by the corresponding angles postulate. Then we have angles 2 is congruent to angle 4. So how did they state angle 2 here congruent to angle 4 here? Well, that goes back to another postulate, the vertical angles postulate. And the vertical angle postulate states any pair of vertical angles, so opposite sides of an x, like 2 and 4, are congruent. So now we know 6 is congruent to 2, and 2 is congruent to 4. So by the transitive property of congruence, we can state angle 6 is congruent to angle 4. Example 2 here. In the figure at the right, they told us line N is parallel to line P. They told us the measure of angle 3 here is 38 degrees. They want us to find the measures of 1 and 2. So what I know is N and P are parallel, M's my transversal, so 3 and 2 are alternate interior angles. And if they're alternate interiors, that means they're congruent because N and P are parallel. So angle 3 is 38 degrees, meaning the measure of angle 2 is also 38 degrees. So I know 2 is 38 degrees. Then I know angle 1 and angle 2 together here are a linear pair, meaning they make the line M. And any line has a measure of 180 degrees. So 180 minus the 38 for angle 2 gives me the measure of angle 1 being 142 degrees. And then we have our 3 theorems split up. So we already had the parallel line theorem, which states if we have parallel lines, or if 2 parallels are cut by a transversal, these 3 things are true. Now you'll see in these, if 2 lines are cut by a transversal so that the alternate interior angles are congruent, then the lines are parallel. So these 3 theorems are the inverses of the parallel lines theorem. So then the alternate exterior angle theorem says if 2 lines are cut by a transversal so that a pair of alternate exterior angles are congruent, then the lines are parallel. And last, if 2 lines are cut by a transversal so the same side interior angles are supplementary, then the lines are parallel. So we're doing the inverse of these 3 statements here. And then we get to example 3. Example 3, the proof here says prove the alternate exterior angles theorem using the figure at the right as a drawing. So they gave us the info, angle 5 is congruent to angle 3. They want us to prove lines M and N are parallel. So 5 congruent to 3 is given. Then they stated angle 3 is congruent to angle 1, right here. How did they come up with that? They used the vertical angle theorem, which says vertical angles are congruent. So 3 and 1 are congruent. Then they stated 5 and 1 are congruent because if 5 is congruent to 3 and 3 is congruent to 1, we can use the transitive property of congruence to say angle 5 is congruent to angle 1. And then 5 and 1 are corresponding angles. So if 2 corresponding angles have the same measure, then the lines are parallel. So that is using the corresponding angles postulate. So it's not one of these 3 theorems, but it's a similar postulate that states if our corresponding angles have the same measure, then the lines are parallel. So the main ideas you can see from these proofs is the idea of parallel lines and then proving a relationship amongst the angles, or a relationship amongst the angles using that to prove the lines are parallel. So to help us in that process, this table here will be important. If you're given parallel lines to start, so if we already know the lines are parallel, then you're looking to use the idea that corresponding angles are congruent, the corresponding angle postulate, or the idea that alternate interiors are congruent, alternate exteriors are congruent, or same side interiors are supplementary, so the parallel lines theorem. So this is starting at parallel lines, working our way toward a different statement. If we're starting with an angle relationship, trying to prove lines are parallel, you would want to look in this column at one of these four postulates or theorems. So the first one, if two lines are cut by a transversal and form congruent corresponding angles, then the lines are parallel. That's the corresponding angle postulate. If two lines are cut by a transversal and form congruent alternate interior angles, so that would be the alternate interior angle theorem to prove the lines are parallel. We can use the alternate exterior angle theorem or the same side interior angle theorem. So this table kind of takes the postulates and theorems from this lesson. If you're starting with parallel lines going toward an angle relationship, look in the left-hand side. If you're starting with angles working toward parallel lines, I would use the right-hand column.